I'm going to be talking about diagonal ASH algebras with stable rank 1, and this is joint work with James Lutley. So I'd like to start by just reviewing some basic stable rank 1 results that are already in existence. So given a unital C-star algebra, we say that it has stable rank 1 if the set of invertible elements in it is dense in the algebra. And in 1990, Mihai Roerdam showed that if you have a simple unital stably finite C-star algebra and you tensor on a UHF algebra, then the resulting tensor product has stable rank 1. This was followed a few years after that by a result of Dederlat, Naj, Nemethi, and Pasniku, who showed that if you have a simple AH algebra with no dimension growth, meaning that there's a uniform upper bound on the dimensions of the spectra of the algebras in the construction, then the limit algebra A has stable rank 1. And a decade or so after that, Roerdam again showed that every simple unital finite Z-stable C-star algebra has stable rank 1. Now, a little bit more recently, another AH stable rank 1 result came into prominence by Elliott, Ho, and Toms, who in 2008 showed that if you have a simple unital AH algebra with diagonal maps between the blocks, then the limit has stable rank 1. And I should say what I mean by diagonal map. So given two compact Hausdorff spaces X and Y, a unital homomorphism going from the full matrix algebra over X into the full matrix algebra over Y is said to be diagonal, provided that there are n continuous functions from the base space of the codomain into the base space of the domain, such that whenever you take an element f of the domain and apply the function phi to it, the resulting function phi of f evaluated at a point y should just decompose as a block diagonal matrix where the blocks are just f evaluated at the various lambda i's evaluated at the point y. And so I should say that this result is a bit in contrast with the DNNP result because there's no assumption on dimension growth. Of course, there is an assumption though on the maps being diagonal, which didn't exist in this previous result. So essentially the result that James and I have is a subhomogeneous analog to this AH result. And the algebras that we're looking at are a certain subclass of recursive subhomogeneous algebras. So I want to talk a bit about them first. So recursive subhomogeneous algebras were introduced by Chris Phillips, and we say that a C-star algebra is a recursive subhomogeneous algebra if it satisfies the following recursive definition. So in the first place, if we're given a compact metric space X and a dimension size n, then we say that the full matrix algebra over the space X into the n by n matrices is a recursive subhomogeneous algebra. And then we build from there. So if we're given a recursive subhomogeneous algebra A, then we can take a compact metric space X, a closed subspace Y of X, a matrix size n, and a unital homomorphism going from the existing recursive subhomogeneous algebra into the full matrix algebra over the closed subset Y. Then we say that the associated pullback with the restriction homomorphism is a recursive subhomogeneous algebra. So we look at all ordered pairs in A plus CXMN, and we take only those for which phi of A is equal to the restriction of F onto the closed space Y. Now, given a recursive subhomogeneous algebra, we can talk about it having a certain decomposition. So if we're given a recursive subhomogeneous algebra A, we know that there must be finitely many compact metric spaces x1 to xl, which are called the base spaces of A, and corresponding closed subspaces y1 to yl, and matrix sizes n1 to nl, and intermediate building block C-star algebras AI, which are subsets of this direct sum, and corresponding unital pullback homomorphisms going from the ith stage building block into the full matrix algebra over yi plus 1, such that the first one is just the full matrix algebra over the first base space, and successively the I plus first step recursive subhomogeneous algebra is just the pullback of AI with CXI with using the unital map phi I as the pullback map. And then the given starting final recursive subhomogeneous algebra is just the final stage building block in this decomposition. Now, of course, if we have a recursive subhomogeneous algebra, the decomposition is not necessarily unique, But when we speak about a recursive subhomogeneous algebra, we're assuming that it comes equipped with a decomposition of this form. Okay, so the subclass of these that James and I looked at are what we call DSH algebras, or diagonal recursive subhomogeneous algebras. And we say that a C-star algebra A is a diagonal recursive subhomogeneous algebra of length L, provided that it's a recursive subhomogeneous algebra of length L with the given decomposition as shown on the previous slide. And that whenever we take a point y in the closed subspace of the I plus first base space, we expect to have finitely many points in the base spaces of the ith stage recursive subhomogeneous algebra, such that whenever we take an element f in the ith stage recursive subhomogeneous algebra and we apply the ith pullback map to it, when we evaluate this at the point y, it should decompose as a block diagonal matrix where the blocks are just f evaluated at the finitely many points that y decomposes into. And of course, these blocks are not necessarily the same size. It'll depend on which of the base spaces the corresponding point belongs in. And essentially, we can just view a diagonal subhomogeneous algebra as so we can view A as a subset of this direct sum of full matrix algebras, where the criteria for being an A is just that this function respects coordinate-wise the decomposition of y. And this is because phi I of f at y is just equal to the I plus first coordinate of f evaluated at y. So any function in this direct sum that respects this for all points in each of the closed subsets of the base spaces will be an element of our DSH algebra. Now, the motivating example of these algebras are the orbit-breaking Putnam algebras. So if we have an infinite dimensional compact metric space T and a minimal homeomorphism H of T, and we let sigma be the corresponding automorphism of CT, so sigma of f is equal to f composed with the inverse of h, and if we let u be the unitary in the associated cross product that implements this sigma action, so uf u star equals sigma of f, for all f in the continuous functions over t, then Ian Putnam looked at at a certain subset of this cross product, where if you have a closed subset S of t with non-empty interior, you look at the subalgebra generated by all of the continuous functions on t, together with all of the continuous functions on t that vanish at S, with the unitary multiplied on the left. And it turns out in 1997, Chinglin and Chris Phillips showed that these kinds of subalgebras are in fact DSH algebras. So these are sort of the motivating examples for such things. Now, if we're hoping to get a stable rank 1 result in the likes of Elliott, Ho, and Toms for these DSH algebras, we need a notion of diagonal maps between such things. So given two DSH algebras A1 and A2 with corresponding base spaces, we say that a star homomorphism psi from A1 to A2 is diagonal, provided that whenever we take a point in any of the base spaces in the codomain algebra, we can find finitely many points among the base spaces of the domain algebra, such that whenever we take a function f in the domain and apply psi to it, and then evaluate psi of f at the appropriate coordinate that x is in, this should decompose as a block diagonal matrix in terms of f applied at the points that x decomposes into. And it turns out that using this definition, we're able to get the subhomogeneous algebra analog results. So if we have a simple inductive limit of DSH algebras that's unital with diagonal maps between the algebras, then the limit has stable rank 1. Okay, so I'd like to talk a little bit about the key ideas that go into this proof. So because it's a stable rank 1 result, we need to show that every element is close to an invertible one. So if we start with a given element, we can assume it's non-invertible. And if we multiply it on the left and the right by unitaries, and then do a small approximation and multiply that approximation on the left and the right by unitaries, and we do this, say, finitely many times, if what we end up with is invertible or close to an invertible, then by unwrapping this approximation, we can conclude that the original starting non-invertible element itself is close to an invertible. And moreover, we can employ the trick that Roerdam used, which is that if you have a nilpotent element, the spectrum of such a thing is just 0. So whenever you add any non-zero scalar multiple of the identity to it, you'll end up with an invertible element. So if we start with a given non-invertible element, multiply it by unitaries, perturb it slightly, multiply by unitaries again, and end up with something that's nilpotent, that's just as good as the original non-invertible element being close to an invertible. So that's the strategy that we basically employ. So we start with a non-invertible element in one of the finite stage algebras in the inductive limit, and it follows that this element must also be non-invertible at one of the points in the base spaces of AI. And then using the DSH structure of AI, we're able to multiply by unitaries and approximate by an element f prime in that same finite stage algebra that looks like this on an open subset of the spectrum of that algebra. So essentially it's going to have the first row and column consisting only of zeros across the whole open subset of the spectrum. And the reason that we want this is then we can use the diagonality of the size in the inductive limit together with a simplicity criterion very similar to the one used in the DNNP and the Elliott-Ho and Tom's paper to conclude that at some later stage algebra in the inductive limit, say the jth stage, and at any point in any of the base spaces there, whenever we look at the diagonal image of f prime and its associated diagonal decomposition, at least one of the points that x decomposes into will lie in U. And this will happen regardless of what point. We can choose J in such a way that regardless of what point x in the base space we look at, one of the decomposition points will always lie in U. But this means, since we know what f prime looks like on U, it looks like this. This means that we can say that essentially at every single point in the base spaces of AJ, the image of f prime in that space will have a zero cross. And what I mean by zero cross is that for any given a zero cross at a given index would just mean that the entire row and column of that at that index are just zeros. So this will happen everywhere at any point that we evaluate the image of f prime at AJ in. And basically, we're able to assume that these algebras in the limit are not finite dimensional, because if they were, the limit would automatically have stable rank 1. So using the fact that they're infinite dimensional, we can essentially use simplicity again to conclude that the sizes of the matrices in each of these DSH algebras must tend to infinity. And as a result, we're able to find a later stage algebra where the image of f prime in the later stage algebra AK, which essentially is just the image of this element here in AK, has many zero crosses at each point. And this is just because when we evaluate this at a certain point in one of the base spaces of AK, it'll decompose as being a block diagonal matrix where each of the blocks is one of these types, but each of these has a zero cross. And so we can go out far enough to get that the image of f prime will have many zero crosses at every point. Now, we don't exactly know where these zero crosses will be, because for a different point, and as we look at different points in the base spaces, we know that we have many zero crosses, but we don't exactly know where they are. Now, what we do know is that because of the block diagonal structure, there's some restriction as to how far away from each other they can lie. So we have some rough idea of where they are, and we're essentially able to multiply the image of f prime in the kth stage algebra by unitaries in AK to obtain a nilpotent element. And we do this by obtaining a matrix that's strictly lower triangular at every point. So I'd like to just say a little bit more about these unitaries in AK that we're multiplying the image of f prime by. So point-wise, what's basically happening is we have many zero crosses, but we don't exactly know where they are at each given point. So the first pair of unitaries that we multiply the image of f prime in AK by, what they do is they put these many zero crosses that we have into tractable locations so that we know where they are. And now we multiply by a second pair of unitaries, which brings all these zero crosses that we have together into the upper left-hand corner, into one big zero block. So this happens simultaneously at every single point. And so because we're looking at f prime, which is the image of f prime in AK, it's going to be a block diagonal matrix at every point. So there's sort of a restriction to how far a non-zero entry can occur from the diagonal. And these unitaries are constructed in such a way so that essentially the size of this zero block will be larger than the maximum distance that a non-zero entry can occur from the diagonal. And so all we have to do is we shift everything to the left so the zero block comes to the top right, and all the non-zero entries now lie below the diagonal. And we do this at every point. And so we end up with something that's strictly lower triangular and hence nilpotent. And the way that these unitaries are constructed, they're basically constructed as being, coordinate-wise, as being products of continuous paths of unitaries where for a given pair of indices, say R and S, in the corresponding coordinate, when we evaluate it at 0, we just get the identity matrix, and when we evaluate it at 1, we get the identity with rows R and S swapped. And everywhere along the path, this would just be the URS evaluated at theta would just differ from the identity at most those 4 entries. So basically, each of the unitaries that we are using are a product of coordinate-wise paths that look like this, where the indices, where the R and S run through almost all of the indices in the matrix. Now, at every point, because the zero crosses occur at different places, we need something that sort of knows where the zero crosses are and tells each of these unitaries when to become a 1 so that they can shift the rows and columns of the zero cross up to the upper left-hand corner. And the way we do this is by constructing an indicator-like function theta in the kth stage algebra, at which we evaluate these above continuous paths. And they tell essentially when, they tell these paths at every point when they should be turning on and swapping the rows and columns. So that's pretty much the idea of, a very rough idea of how this proof goes, minus a lot of technical details. And we obtain a sort of nice corollary to this, and this was initially a conjecture of Don Archie, Chris Phillips, and Zhuang Yu, which is that if you have any infinite compact metric space T and a minimal homeomorphism of T, then the associated dynamical cross product must have stable rank 1. And this follows by just taking an element X in the metric space T and then observing that the associated Putnam algebra, Putnam subalgebra, the orbit breaking one of the singleton set X, is in fact a simple inductive limit of DSH algebras with diagonal maps. And so it turns out that this subalgebra has stable rank 1, and hence by a result of Archie and Phillips, the cross product itself has stable rank 1 since this subalgebra is centrally large in it. Okay, so I guess I finished a little early, but that's all I have to say. So thank you very much for listening.